Welcome all of you. In the last 2 or 3 classes, we discussed extensively two-dimensional NMR spectroscopy, where we discussed about correlation type experiments, especially homonuclear correlation, heteronuclear correlation like COSY, TOCSY, HSQC, and inadequate for correlation of the dilute spins. Varieties of examples we took, and we also understood in some specific examples like COSY, what is the phase of diagonal peaks, how do they come, how do cross peaks come, what are their phases, and how we can overcome some of these problems by going to variants of the COSY type experiments. That is what we discussed. And later I discussed TOCSY, in which I said COSY identifies immediate coupled neighbors and you have to go systematically step by step ladder, whereas TOCSY identify all the coupled spins of a spin system in single experiment. There we also discussed it is similar to COSY, but in the second pulse we are applying what is called spin lock pulse. It is called for isotropic mixing. Then what is going to happen is the spins lose their identity. There won't be any chemical shift evolution, only they will be coupled among themselves, and as a consequence there will be transfer of magnetization to one another in the coupled spin system. And this is what we understood, and we went to heteronuclear correlation, took the example of carbon coupled to proton, especially the inverse experiment HSQC. What happens for a coupled HSQC and a decoupled HSQC? How do you do the long range correlation like HMBC, where in the case of HMBC experiment, long range correlations are retained, short range correlation, one bond CH correlation like what we do in HSQC are suppressed. This is a fantastic experiment where it helps you in identifying connectivity among long range correlation of carbon and protons. Then we went to inadequate experiment where we discussed about correlation of dilute spins like carbon 13, where I said again it is a very simple experiment. We have to adopt the double quantum selection pathway, where we use a double quantum filter, and using the double quantum filter we will ensure that each carbon will which is coupled to its neighbor. So these two coupled carbons will give rise to cross peak at some of their chemical shifts in the F1 dimension. So the easy way to identify the inadequate spectrum is go horizontally, then vertically. You will find out from the cross peak, and then again go horizontally. You will find the next coupled partner. Like that, systematically and ladder wise, you can go step by step and identify all the carbons of the spin system next to each other. So with that, we wanted to discuss something more. There are many interesting 2D experiments which can be utilized in the daily life, like NOSY, J-Resolve, and ROSY. Because of shortage of time, I did not cover that, and I will see in case if the time is there at the end, maybe 1 class or 2 class. If there is time, I will come back and start that. Otherwise, it is all identically pulse sequence, everything we know how to understand. You can go through that. If there is time, I will come back. So today I will switch over to a different topic, which is called multiple quantum NMR. It is something different from conventional one-dimensional single quantum NMR what you people have come across. Like for example, any spectrum you are going to take in the routine day-to-day experiment you do in any NMR spectrometer laboratory, they are most of the time are one day single quantum spectrum, whether it is 1-dimensional, 2-dimensional, 3-dimensional, and anything other than one single quantum are forbidden transitions in NMR. That is what I said in the very first class. And we will continue today and see how we can detect such transitions, something which are forbidden. Somehow intelligently if you can detect it, it has a lot of advantages. So in this class what I am going to introduce to you is multiple quantum NMR. This has several applications, we can utilize it in some way. So we will start with that today and understand what is multiple quantum NMR. Okay. First of all, let us start with the selection rules for transitions. A single spin off nucleus, if you consider, we have beta state and alpha state, minus half and plus half. This very first class in the first course and this course we discussed. And each state has, or the energy level has a characteristic magnetic quantum number, that is beta and alpha, corresponding to m equal to minus half and plus half. And the difference delta m is plus 1 or minus 1. And then I said in the beginning, I will repeat, when there is a change in magnetic quantum number between two energy states is plus 1 or minus 1, then transitions are allowed. Such transitions are allowed. All transitions where change in the magnetic quantum number between two energy states is either plus 1 or minus 1, that is allowed transition in NMR according to the selection rule. So these are all allowed. That is why they are called single quantum transitions, where delta m changes by plus 1 or minus 1. For example, change any spin, even if I have taken an example of a single spin, you can take even more number of spins, not necessarily 1, 2, 3, etc. That is what we discussed earlier also. So if you have two coupled spins, any one of them can switch state to alpha to beta or vice versa. That is allowed. That is also single quantum. So this is what conventionally we detect in NMR routinely. This is delta m equal to plus 1 or minus 1. They are called single quantum transitions. Remember, the delta m equal to plus or minus 1 are single quantum. Delta m not equal to plus or minus 1. Remember this one, not equal to plus or minus 1 are called multiple quantum transitions. Anything other than that, it could be even 0 here. 0, 2, 3, 4, 5, anything. So they are called multiple quantum transitions. And these are forbidden transitions in NMR, and you are not going to detect them. Okay. So let us see what are single quantum transitions and multiple quantum transitions. Of course, explicitly, this single quantum transition by the energy level diagram of the two coupled spin system also we discussed earlier. Again, let me repeat. Now consider two coupled spin system A and X. Now there are four possible orientation of the spins, product functions if you consider. With quantum mechanical analysis also we did this. Now there are four energy states corresponding to beta beta. This is A is beta, X is beta. Two possible, both the spins are down, or alpha beta and beta alpha. This is up, this is down, or this is down, this is up, or both are up, alpha alpha, alpha A and alpha X. And we know the total magnetic quantum number for each of these energy states is minus 1, 0, 0 and plus 1. Now according to the selection rule, single quantum transitions are allowed. Delta m, change in the magnetic quantum number, should be equal to either plus 1 or minus 1. So that means any one at any given instant of time, a single spin is going to change or flip from alpha to beta or beta to alpha. For example, this one. Here A spin is changing from alpha to beta and beta to alpha. This is allowed transition. This corresponds to A transition. Similarly, here alpha A is changing to beta A and beta A is coming to alpha A. This is also allowed transition. It is A transition. Now look at the other one. Here alpha X is changing to beta X and beta X is coming back to alpha X. Again, change in the delta m is equal to plus 1 or minus 1. Allowed transition. This corresponds to X transition. What other transition is possible here? Look at it, this one. So here alpha X is again changing to beta X and it is delta m equal to plus minus 1. So this is also allowed transition. So this is again X transition allowed. Okay. So in the single quantum transitions of two interacting spins, two coupled spins, we have only four possible transitions. You can look at it, no other transitions are allowed here. So in a two spin system, you can get maximum four transitions. This is what we observed. In the analysis of AX and AB, we saw that there are four transitions allowed when two spins are coupled. So 2 peaks you get for A and 2 peaks you get for X. Fine. So if I have n coupled spin systems, in any if in a coupled spin system, then how many single quantum transitions we can get? It is given by 2n C n minus 1, where n is the number of coupled spins. in a spin system. And analysis of such spectrum gives me n chemical shifts and n into n minus 1 by 2 couplings. So, this is very important. If I have n coupled spin system, this many number of transitions are allowed or detected, and analysis of such a spectrum gives me only n chemical shifts and n into n minus 1 by 2 couplings. Okay. Now, if I have a coupled spin system and with the derivable information and the number of allowed transitions for different spin systems, let us see different size of the spin system, coupled spin system. Let us see how it happens. Now, let us say 3 spins are coupled. What is the maximum simple single quantum transitions that are allowed? Of course, strictly speaking, 2n c n minus 1 if you put, it should be 15. 2n c n minus 1, if you see it, n is equal to 2 into 3 6, c n minus 1 is 2, 6 c 2, factorial 6 or factorial 4 into factorial 2, this will become 6 into 5 divided by 2, it is 15. So, it has to be 15. Of course, in a weakly coupled case, I have written 12, 3 are combination transitions will not be seen. In practice, in reality, theoretically, you should get 15 transitions for 3 spins. And number of couplings, you have to derive how many? 3 spins are coupled, let us say 1, 2 and 3, you get 1, 2 coupling, 2, 3 coupling and 1, 3 coupling. Only 3 couplings you have to derive. And how many chemical shifts you have to find out from this? 3 spins, 3 chemical shifts, the 3 are chemically inequivalent. So, there are 3. So, you have to get 6 parameters from 15 transitions. Not bad, reasonably okay, not a complex spectrum. Just go by one more spin. Let us consider 4 coupled spin system. It gives us a 56 transitions. 56. And how many parameters you have to determine? You have to determine 4 into 4 minus 1 by 2, which is equal to 6. You have to get only 6 couplings and 4 chemical shifts. So, you have to determine only 10 parameters, but you have got 56 transitions. That is also tolerable. Go to the next one. 8 coupled spin system if you go, you will get 3003 transitions, you determine only 28 couplings and 8 chemical shifts, that is all. For just to determine 36 parameters, you have 3003 transitions in the 1D spectrum. What does it mean? Single quantum transitions are highly redundant. There are more transitions than what is required to derive the spectral information. That many are not needed for us. Why do we require 3003 transitions to determine only 36 parameters? That is why single quantum transitions are highly redundant when you want to analyze and derive the spectral information. Let us understand how it is. Look at simple 3 spin case. I take the example of AMX, weakly coupled spin system. I consider a situation JAM is greater than JAX greater than JMX, and this is a chemical shift of A, chemical shift of M and chemical shift of X. As I said, 3 spins should give 15 lines. In a weakly coupled case, we are getting 12 lines. Fine. Even these 12 lines, we can have 2 solutions to determine chemical shift and coupling constants. Look at this one. This separation gives me JAM and this separation gives me JAX. I am looking at A and M and X are the passive spins. I get JAM and JAX. And look at M, I get JAM here and here JMX. And if you come to X spin, this is JMX and this is JAX. So, we are going to get 2 couplings at each chemical site. At the chemical shift of A, you get 2 couplings, M, you get 2 couplings, at delta chemical shift of X, you get 2 couplings. Fine. All 6 couplings and all 3 chemical shifts we derived. Fine, that is understandable. I mean, all 3 couplings and 3 chemical shifts. Now, look at it. Here itself, JX you can get from here, you get from here. MX you get from here, you get from here. AM you get from this one and also from this one. Already, the redundancy of information. You can get already in the two places. If you analyze this, there is one possible solution. You can get JAM at two places, MX at two places, two separations. JX will give, you get from two separations of at the chemical states of A, M and X. So these multiplicities will give coupling information, but there is a redundancy of the information content. Now, what happens? Can I get this information by some other way? Again, this is also possible. This also gives me JAM and this also gives me JAX. Again, this will give me JAM, this will give me MX, and this JAX and this will give me MX. So that means again you have a second solution, you can get this coupling from other splitting separations also, but again there is a redundancy of information. What I am trying to say is simple single quantum NMR spectrum, there is so many transitions, even for 3 spin there is a redundancy of the information. Transitions are highly redundant. We do not require that many to derive the required information. So with this, now I will introduce what is called an active spin and also a spectator spin, which is nothing but a passive spin. As far as multiple quantum is concerned, we know we introduced active spin and passive spin earlier. We discussed that. Active spin is the one which is undergoing the flipping at any given instant of time, and passive spins are not involved in the transition flipping, but it will give rise to coupling with the active spin. That is what I said. Okay? When I consider the spin system, at any given instant of time you can flip one of the spins and it will couple to remaining passive spins which are just watching it, and that gives rise to coupling. So the spins will undergo flipping. When it undergo flipping, at the chemical state position of that, it gives rise to coupling with the passive spins. This is what the important information which we discussed active spin and passive spin long ago, and even in the first course and this course also we discussed active and passive spin. Now that was for the single quantum transition. Let us say what are active spins and passive spins when it comes to multiple quantum. Okay. Now let us say I have group of coupled spin systems like this. There are so many spins are coupled. I am going to flip only one of them which is colored in blue from alpha to beta. Now as far as I am concerned, this is active spin. All the remaining spins are passive, but they form a coupled spin system. They are all coupled among themselves. One of the coupling here may be 0, does not matter. This could be 0, but overall they form a coupled spin system. So it is only single active spin is there, and there are many passive spins here. This is nothing but your single quantum. That is what you see in the single quantum NMR. Now look at this one. Supposing if I am able to flip all the 3 spins here at a given time or at a time simultaneously, then there is a coherence transition. All the 3 will be simultaneously undergo transition. Then what will happen? Now these are the active spins, 3 are active spins. Many active spins are there. Together with them they are flipping. I will call it a super spin. No problem. I will give on my definition, it is a super spin. And there are many passive spins again. Here many passive spins are less compared to single quantum because more spins are flipping at a time. And these are called spectator spins or passive spins. So remember, in the single quantum at any given instant of time, only one spin is flipping from alpha to beta or beta to alpha, whereas in the multiple quantum many spins are flipping at a time and there will be less passive spins. This is multiple quantum transition. Now transitions other than delta m equal to +1 or -1, let us see how we can detect what are they, not how to detect what are they. Again let us consider the example of 2 spins, 2 coupled spins. Now 4 possible spin states and the total quantum number, magnetic quantum number of all of them. For example, this is -1, +1, 0, 0. Now as I said, simultaneously beta beta to alpha alpha spin can undergo transition. This is allowed. Sorry, not allowed. You see, look at this one. This is not allowed, but still let us say if this transition is allowed, what is the change in the magnetic quantum number between these 2 states? +1 and -1. So it is plus or minus 2. It is a forbidden transition. At a time, since 2 spins are flipping, it is called double quantum. Double quantum transition is the one where simultaneously two spins will be flipping from beta beta to alpha alpha or alpha alpha to beta beta, and the change in the magnetic quantum number is either plus 2 or minus 2. Okay. Now, zero quantum, let us see. This is, we saw, this is minus 1, 0, 0 and plus 1. Now, I can think of a situation. Is it possible to make the spins undergo transition simultaneously, alpha beta to beta alpha like this? Alpha alpha, alpha beta here can go to beta alpha. Is it allowed? It is not allowed, because change in the magnetic quantum number is 0, 0 to 0. The transition is forbidden. But somehow if I detect that, then it is called zero quantum, because change in the magnetic quantum number is 0. So, in the two coupled spin case, we have possibility of detection of one double quantum and one zero quantum, in addition to 4 single quantum. That is possible. See, so this is what is called the zero quantum transition, and this is the double quantum transition. Both of them in two coupled spin case gives single peak transition. Only at single frequency we get a peak. So, the direct detection of coherences between the states other than delta m equal to plus or minus 1 are forbidden, and MQ transitions you have to detect only indirectly. There is no direct detection of MQ transitions. Indirectly we can detect it, that is possible. And if you detect that indirectly, it has numerous applications for you, and we will touch upon, we will discuss more about multiple quantum and then touch upon one or two applications in this course. So, now you may ask me a question, can I detect MQT in every molecule? Is it possible? That question can come, but remember, there are basic conditions. All the spins should part of a coupled spin system. I told you, I have, let us say, 5 spins. All of them should be coupled among themselves. 1, 2, 3, 4. 1 is coupled to 2, 3, 4, 5. 2 is coupled to 1, 4, 5. All those things. One of the coupling strength may be weak or 0, doesn't matter, but they should form a part of the coupled spin system. Then we can detect MQT. That is one of the conditions. Secondly, the coupling should be reflected in the spectrum. For example, if I go to the magnetically equivalent spins or chemically equivalent spins, you may have a J coupling, but you do not see that in the spectrum. An example like this. Look at this, it is ethylene molecule. As far as you are concerned, if you look at the isotropic NMR spectrum of this molecule, you are going to get a single peak, because all the 4 protons are chemically equivalent here. But if you look at any proton, each proton experiences 3 couplings. It can couple to this proton, it can couple to this proton, and it can couple to this proton. Similarly, if you go to this one, this can couple to this can couple to this can couple to this. Each proton experiences coupling with the remaining proton. There are 3 couplings for each proton, and all of them are identical. 3 couplings are different, but each proton experiences identical 3 different couplings. Look at the benzene molecule again. Here, one proton can experience an ortho coupling like this, a meta coupling like this, and a para coupling like this. Go to this one, same, it experiences again this proton, ortho, meta and para. Come to this one, ortho, meta and para. Each proton there experiences 3 different couplings. All the 6 protons here experiences 3 different couplings of similar strengths. All of them will experience same ortho couplings, same meta couplings and same para couplings. And look at this simple molecule, pyrazine. Here this is one coupling, this is one coupling, and this is one coupling. Each proton again experiences 3 different couplings. They are all chemically equivalent. But if you take the isotropic NMR spectrum of any of these 3 molecules, how many peaks you get? Only 1 peak. 1 peak for this, 1 peak for this, and 1 peak for this. So, such type of molecules will not give rise to NMR, MQT. So no MQT is detectable in such systems in the isotropic phase. I am stressing this point, in the isotropic phase, because if you dope this molecule in a partially ordered system, you bring in another parameter of NMR called dipolar couplings. If there are dipolar couplings, interestingly we can see coupling among all of them, and it will be reflected in the spectrum, dipolar coupling. Then you can detect MQT, no problem. But in the isotropic phase, no MQT is detectable in these type of systems which are chemically equivalent or magnetically equivalent, and the couplings are not reflected in the spectrum. Please understand this. Now we will go to the barrier to the highest quantum. Which is the barrier to the highest quantum? For n coupled spins, the highest quantum detectable is nth quantum. For n coupled spin system, maximum you can get is nth quantum. You cannot get beyond that. Okay, that is the barrier to the highest quantum. So how many such quanta you can detect if I have n coupled spin systems? For n coupled spins, one can get n plus 1 different types of multiple quantum. N highest is n. For n coupled spin system, highest quantum is n. Then where do we get n plus 1? Remember, n minus 1 etc., but 0 is also included. 0 quantum also you can get. So as a consequence, if there are n coupled spins, you can get n plus 1 different types of multiple quantum. What do you mean by different types? As we go further, I will discuss this with you and I will tell you. Okay. Even in the double quantum or n minus 1 quantum, n minus 2 quantum, there could be varieties, different types of n minus 1, n minus 2, n minus 3. Different spins may be undergoing and flipping like that. Okay. The flipping of the spins, the active spin always experience a local field due to the passive spin. This is true even in the single quantum. If one spin is undergoing flipping from let us say beta to alpha, then it will experience, it is coupled to the other spins which are passive spins sitting next to it or J coupled to it, these passive spins which create a local field at the site of this at the site of the spin. The local passive spins will create a local field at the site of the active spin. So it experiences that. That means this active spin is coupled to passive spins. That is important. Please understand, the active spins are always coupled to passive spin because it creates a local field at the side of the active spin. So local field for the nth quantum is what then? There is no local field at all because there is no passive spin. All spins are active spins. If I have 4 spins coupled among themselves, if I go to 4th quantum, there is no passive spin. That means there is no J coupling. Then where do these all these things come? All 4 of them are flipping at a time. There is a coherently all the 4 will undergo flipping. Then where do this peak comes? It comes only at the sum of their chemical shifts, because the local field is only the chemical shift and not the J coupling. All of them are flipping at a time, at this local field is the sum of their chemical shifts, all the 4. So that is what happens. So nth quantum appears at the sum of the chemical shifts of n spins, and in the nth quantum there are no passive spins and no J split multiplicity. That means how many peaks we get? Simple logic, nth quantum, because all nth coupled spins are simultaneously changing from alpha 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 to beta 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 and vice versa. Since there is no other passive spin, you get only single peak. So nth quantum always gives a single peak at the sum of the chemical shift of the coupled spins. Please remember this. So we will now understand evolution of chemical shift and J coupling in double quantum and zero quantum excitation in a weakly coupled 2 spin system. How it works? What will happen if I want to see double quantum and zero quantum in 2 spin case, and how chemical shift will evolve, how J coupling will evolve, and then we will take the example of the 3 spin. So now since the time is getting over, what I am going to do is, since time is getting over, I will take up this in the next class. Right now what I want to tell you is today I started introducing the multiple quantum NMR. Basic point I wanted to tell you is for the basic condition to see a multiple quantum is all the spins should be coupled among themselves. It should form part of a coupled spin system and the coupling should be reflected in the NMR spectrum. And these are the transitions, multiple quantum transitions are the ones where the change in the magnetic quantum number between the energy different energy states is other than plus minus 1. It is not plus 1 or minus 1. Other than that, it could be plus or minus 2, plus or minus 3, etc. or even 0. Plus or, these are called multiple quantum transitions. In the conventional NMR, what you detect is a single quantum NMR, and these multiple quantum transitions are forbidden. As a consequence, you cannot detect them. So, what we detect in the conventional day-to-day NMR experiment you do are single quantum NMR. There are single quantum transitions. And also I pointed out single quantum transitions are highly redundant. There are more transitions in a coupled spin system than required to get the spectral information. For example, if I want to analyze, let us say 8 coupled spin system, how much I have to get? I have to get how many information I should get? I must get 56 couplings and then 8 chemical shifts, whatever that small number. But how many transitions are allowed? Which is given by 2NC(n-1) formula. It is 3003 transitions. Why do we require 3003 transitions to get only small 8 chemical shifts and only 50 or 60 J couplings? It means single quantum transitions are highly redundant. So if you go to higher and higher quantum, you will have less transitions. Simple, you took the example of a 2-spin case. 2-spin J coupled. How many double quantum are there? Only 1. How many 0 quantum are there? Only 1. But how many single quantum are there? 4. As a consequence, you must understand as you go to higher and higher quantum, the number of transitions what you can detect drastically comes down. We will observe that, we will see that later. And then barrier to the highest quantum of n coupled spin system is nth quantum. And in the nth quantum, there are no local fields. So all the spins are simultaneously flipping from alpha 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 to beta 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 states and vice versa. As a consequence, the local field is only the chemical shifts. So the nth quantum spectrum of n coupled spins will give you a single peak at the sum of the chemical shifts of all the coupled spins. So now we can understand what will happen, how the double quantum excitation occurs, 0 quantum excitation occurs for 2-spin case, 3-spin case, etc. And then how we can utilize them to solve or utilize them to understand some of the important problems chemistry. How can we use this method to derive some information? We will come to that later. I will stop here today and we will come back and continue with this in the next class. Thank you.